This lecture is the second part of multi-unit systems when we do not have chemical reaction. So what we're going to look at here is how we can perform balances around any set of the units we choose, simply by drawing our box around them. So we looked at this process, and we could draw our box just around the mixing unit, in which case we would be dealing with streams N1, N2, and N3 for our balances. We could draw the box around the separation unit only, and then we would only be dealing with streams N3, the product stream, and the gas stream. We could also do the overall balance by drawing our box around all the units present, and this would be the total plant input and output. So we would have N1, N2, the gas stream, and the product stream. So when we draw our box around all of the units, then this stream is not included in the balances. So the next thing we need to look at is recycle. Recycle is dealt with exactly the same way we deal with systems that don't have recycle. We simply have to pay attention to the direction of the arrows going into or out of the boxes that we choose. So we're going to look at an actual process, and we're going to do the calculation. So if we look at the system just with the distillation column, we have F1, F2, F5, and F4 to deal with. Note that the arrow here of F5 is an input and F1 is an input. If we do the overall balance, then we do not have the recycle stream as part of our balance calculation. We only have F1, F3, and F4. So let's do a calculation. We have here ethanol and water, and we want to dry out the ethanol. So the goal is we have some unknown amount of ethanol being fed, and we know a little bit about the various streams. We know what's coming out of the distillation column is 4% ethanol and 96% water. And we have coming out of the top of the distillation column, we anticipate a higher composition of ethanol, probably at the azeotrope that forms when you distill ethanol in water. Then we're going to put that through a molecular sieve where we dry it out much further, and we end up getting a product of 99.5% ethanol with only 0.5% water. So we know this stream flow rate, we know this stream flow rate, we know this stream flow rate, we know mole fractions here, so we know everything about this stream. And we know mole fractions here, but we don't know the flow rate. So we can look here at, we're going to look at the degree of freedom analysis and try to identify what would be the best place to do our balances. So if we look at the distillation column, we have 3 unknowns, and we can do 2 balances. If you look at the adsorption column, we have 3 unknowns, and we have 2 balances. If we look, however, at the overall process, we have two unknowns only, and we can do 2 balances. So this is going to be our choice to proceed with the calculation. So if we do the overall balance, we can solve for F3, and then we can solve for the mole fraction of ethanol in stream 3. We can then do the balance around the molecular sieve column. And if we do the overall balance, we solve for F5. And then we can do an ethanol balance to get the mole fraction of ethanol coming out of the distillation column. And then we can do the ethanol balance around the distillation column. And this is redundant, okay? But luckily, we end up with this 5.68 is equal to 5.68. Depending on how you set it up, you may get a different set of two numbers there, but the key is that when you get something like this, it shows you that your calculation doesn't lead you to any new information. Okay, so the summary, when we do balance calculations without reaction, draw and label the flow chart, label the unknown flow streams, carry out a degree of freedom analysis, and find one unit or set of units or balance where we find 0 degrees of freedom. Then we can make calculations, and that you then can move to other units with the new given information that you have found. Then you solve all the unknowns to complete the flowchart, and again, check your answer using an additional balance or test of reasonableness. What I want to show you here is what is a purge stream. Generally, purge streams are used when you have a reaction, and the reaction may have an inert. And this is relatively common for different reasons, that you have some inert component in the reaction. And what happens when you have an inert is that if you don't have a purge stream, the inert may build up in the process and could cause a safety hazard by exploding or something else. So you have a purge stream as a way of releasing some of the gas, and that allows you to remove the inert excess from your process. So one other thing I want to point out is I have named all of these locations for you to see. Fresh feed is the one coming in. It's like coming in off the truck or the train car or however it's being delivered to the plant. That may be mixed with the recycle stream, okay? So I've drawn the recycle stream and the purge stream in the same color box because they have the same composition. How do you know that? You're just bleeding off some of the stream. If you're bleeding off the stream, it has the same composition as what you bled it off from. So that's important to recognize. However, the reactor feed, or the feed to the reactor, has a different composition from both the fresh feed and the recycle stream. You add the recycle stream to the fresh feed, and that gives you the feed to the reactor. So pay attention to that when you draw your flow charts. This stream here may be referred to as the reactor effluent. Effluent is what's coming out of the reactor. And here we have process effluent coming out of the entire process. We can have, there's two kinds of points, and I'm going to identify them here. We have a mixing point where you have two streams going into one stream, and we have a splitting point here where you have one stream going into two streams. Okay, so this is your quiz problem to look at solving multi-unit balances. And note here, I've carefully labeled all the unknowns for clarity. And this here is W1 and this is W2. And I've identified in the problem that there's W1 does not equal W2. So But there's enough information here for you to solve this problem.